Yeah, please. For how many of you it has been covered?
So in our BTech, we have studied the infinite slope part and only a few of the finite slope part.
Achha, okay. So for you, a bit of it has been covered.
Yes.
But anyhow, achha. And what about during your master's program?
In the master's program, we have covered the Bishop's method and Bishop's method only mainly. The Morganson price and every other method was not covered in detail.
Okay, no issue. And what about for my MTech students? For any of you?
Only little bit knowledge in BTech, sir. Not that good.
Okay, so no problem. So let me take up in a detailed way the next chapter, that is the stability of the slopes. So when we talk about the stability of the slopes, so we normally talk about a few of them. So we have, so based on our knowledge in the undergraduate program, we have tried to understand what is a slope, and before that you need to understand what is a landslide, because this is the quite often a term coined by several people. So without having understood what is a slope or what is slope stability, but even a non-engineer also can coin a term called as a landslide. So in general, if you look at carefully, so landslide is a terminology that has been given for movement of the soil in the downward direction. Okay, that is the general definition that we can accord to a landslide. But when we talk about the landslide, or when we deeply analyze what caused the landslide, then we end up at the point where we need to understand something like a slope stability or slope instability. So these are the two things. So if the given slope is stable, then we call it a stable slope. Otherwise, it is called as the unstable slope. So unstable slope, so depending upon the type of the structure. Suppose if it is an infinite slope, then it may trigger or it may cause the landslide. While if it is a finite, like an earth dam, where the height is a couple of meters, then we call it as a slope or embankment failure or the slope failure. So here you can see a couple of the examples how the finite slope is distinguished from the infinite slope. So in the first picture you can see the infinite slope, then an earth dam, a finite slope. So then the slope stability caused by another factor, that is the water flow. So within the soil, that is because of the seepage, or so the slope instability may be because of the sudden drawdown, or the slope instability may be because of the earthquake loading conditions. A few of the causes here has been shown. But when you talk about the slope stability, there are two important terminology that you must understand. So both are synonyms only, but there is a mild distinction between them. So thereby we define the factor of safety. So these terminology are called as a, one is shear stress. The first one is shear stress, while the second one is shear strength. So if you can able to distinguish the sensitive difference between the shear strength and the shear stress, you can understand a lot about the stability of the slopes. Okay, let us try to understand what is the difference between the shear stress and the shear strength in this chapter, and how to determine the factors. Suppose if anybody is asking, how do you define the factor of safety? So that is defined as a resisting force divided by the driving force. That means there are two forces that are there which are causing the slope for instability. Now, suppose if I take an example of this case, let us take a small example of an earthen dam. So here, this thick dotted line indicates the geometry of an embankment, while this dotted line, which is indicated below the embankment, is called as a failure surface. This is failure surface. Now, here also indicated with an arrow, that is called as a component of an earth. component of an earth. So usually it is indicated in the downward direction because of the gravity. So we can say this is weight of the soil, within the geometry of A, B, and C. Within the geometry of A, B, and C. While the external surface, that is the thick line, is a fixed line or the fixed boundary. While the dotted line, that is called as a failure surface or the failure envelope, is not a fixed. So your entire aim of any slope stability chapter is that you need to find it out what is the probable location of this dotted line. So when I say this is a failure surface, now this failure surface is differentiating two soil masses of the same soil. The soil above the dotted line and the soil below the dotted line. The soil below the dotted line is intact and not subjected to any downward movement. While the soil which is above the dotted line, so it is undergoing some kind of the translational or rotation motion, or per se, you can simply say that it will be subjected or it is subjected to some kind of the downward movement. A chunk of a soil within the geometry of A, B, and C will be subjected to some downward movement against a fixed failure surface. Now just imagine the failure or the movement of the soil chunk above the dotted line. It did not start immediately. This is the first thing. That means the construction has done, and after some time the failure might have started, or the failure or the movement of the chunk might have started at the end of the construction or during the construction. Now the movement is against this dotted line. That means before the movement, some kind of a force is resisting the movement of this child chunk. So if you understand very carefully, the downward movement of the soil mass, that is weight W of A, B, C, is resisted by something all along the failure surface in the opposite direction. So this resistance is called as a shear strength. This resistance is simply designated as shear strength. And what about the soil chunk of ABC which is moving downward? This moving downward weight that develops something called as a shear stress. I hope it is now clear to everyone the difference between shear strength and shear stress. Now if I ask you to define the factor of safety, it is very simple. Shear strength upon shear stress. So shear stress is going to be developed with time, while the shear strength, that is the resistance, so which is developed against the shear resistance or the shear stress, is a fixed component. Okay, so therefore when you define the factor of safety, we always say one term is fixed, another term is variable. So here shear strength is fixed while shear stress is variable. So if you look at otherwise also, when we define the factor of safety value, we always say for a stable slope, the factor of safety should be always greater than 1. When we say the factor of safety is 1, it obviously indicates that it is on the verge of the failure, because your shear stress component is equivalent to the shear strength component. So the moment a slight increase in the shear stress, it causes the destability or instability, so resulting in downward movement of the geometry of the soil A, B, and C. Okay, so therefore, in order to ensure the safety and stability of an embankment, so it must be ensured that the factor of safety is higher than the 1. That means the shear strength is much higher than the shear strength of the soil. Okay, so this is a very simple funda in defining the factor of safety. So this also I told, and so there are two things that we have understood from your undergraduate program. One is natural slopes. Next is man-made slopes. Natural slopes is called as a infinite slope, while man-made slopes are called as a cuts and embankments, cut or fill or the embankment, whatever it is. So here you can see different examples of the natural slope: hillsides, mountains, river banks. All these fall under natural slope. Man-made slopes, fills at the dams, canal banks, excavation sites, trenches, highway embankment. All these fall under the man-made slopes. So while in the natural slope, the length is infinite, while in the man-made slope, the length is known to us. That's why it is definite slopes. So there are different causes for the slope instability or the landslide or the slope stability. So these things also known to you. So a couple of the fundamental reasons are the erosion or the landslide. Landslide means again slope instability only, or simple movement of the soil. There are some other terminology also, so that I will explain. And as I told, there are two things. One is shear strength, next is shear stress. So it is desirable to understand what are the different factors that are contributing for the increment in the shear strength or decrement in the shear strength or variation in the shear stress. So in this slide, a couple of the factors which are causing improvement in the shear stress has been listed out. Now, one thing you need to understand here is, suppose if the shear stress increases, what will happen to the factor of safety? Will it increase or will it decrease?
Sir, repeat question.
What happens to the factor of safety value if there is increment in the shear stress?
So factor of safety will decrease.
Factor of safety decreases. Now, when you look at these list of factors, you should understand that any improvement or some kind of the perturbation in these factor causes improvement in the shear stress and thereby decrement in the factor of safety value. So therefore, when you analyze any slope, you need to understand that nothing is happening to these factors which are causing increment in the shear stress. Similarly, there are often you also need to encounter some other conditions where we need higher or lower shear strength. So either you can play with low shear stress or high shear strength, vice versa. So here you can see some of the factors which are causing the low shear strength. So there are factors which are causing the highest shear strength, which are not desirable. There are a few more factors which are causing the low shear strength, which are also not desirable. Now, what are those factors? They have been listed here. So when you understand that the shear strength is decreasing, then you may take a small attention to what is happening to these different factors, which is causing decrement in the shear strength. For example, composition and texture of the material, physicochemical reactions, effect of the pore water, change in structure, vegetation, so on and so forth. So these any variation in these factors will cause decrement in the shear strength, thereby decrease in the factor of safety value. Besides the slope stability or the slope failure, a few terminology that you need to understand, those are called as a fall or topple or slide or spread or flow. So these terminology are valid for geotechnical engineers as well as geology engineers, geology or geological engineering. So the people who deal with hills or the deeper soil strata, so they normally deal with all these terminology. Okay, now in this chapter we typically deal with something called as a slide. But if you deal with the rock mechanics, then we may understand that apart from the slide, we also may have to deal with the fall, rock fall. While topple, this is something else which may be valid for both soil and the rock as well. Spread, this is typically valid for the soil only. Flow, this is also valid for the soil, but this is also valid for any other material which can able to flow. Let us try to understand. So rather than this one, yeah. Now try to understand. This is the fundamental definition of the fall. Fall means this is the detachment of the soil under the rock, and that detached fragments will fall from a certain height, as shown in this schematic. So this is the basic definition of a fall. Now, just try to compare yourself the definition of the fall with the slope instability. In slope instability, there was no falling down of any detached mass. It is a continuous sliding of the mass. Next definition is a topple. So this is, here you can see there are different fragments of the rock or of the soil. So if one fragment moves forward in a rotational way, so then that is called as a topple. So this is a forward rotation of a soil or the rock mass about an axis below the center of the gravity of the mass being displaced. That is called as a topple. So the topple normally happens for a bigger chunks. It will not happen like for example soil. It is a particulate material. Then the typical terminology that is valid in this chapter is slide. So here a big soil chunk or the soil within a particular area, so that slides in the downward movement or in the downward direction. This is downward movement of a soil mass occurring on a surface of a rupture. So that's what is called as a slide. Now another definition is a spread. So this is a form of a slide by translation, but it occurs so when there is a sudden movement of water bearing seams of the sands or the silts overlain by a clays or loaded by a fills material. That means there should be something, a loose material shall exist at the bottom of the denser material. Then only a spread can occur. Then the last one is called as a flow. So if you look at this schematic and when you compare this with the landslide, so you can easily understand. A flow can occur for a soil, but when it is mixed with significant quantity of the water. Now the resultant mixture is so viscous and dense that causes something like a flow, but not flow of water. So it leads to something called as a viscous fluid flow. That is called as a flow. But when the sliding is happening, so the sliding is caused by certain area of the soil chunk. But when you talk about the flow can originate from a particular point, and that phenomenon continue for a certain period of a time, because this is something like a viscous flow. So this is how you can able to distinguish between different failures like a flow, spread, slide, topple, and fall. If you go to Himalayas, so you can see all these sorts of the failures. A failure of a rock fall, sliding of a soil mass, or toppling of a rock mass of the soil, or spreading of rock mass of the soil, or flow. Anything can happen. All these can be seen if you go to Himalayas. The best example of the flow is recently an incident occurred in Japan. That is called as a mud flow. If you see any YouTube video, just couple of months only it is happened. So if you see the video of that mud flow, that typically falls under this flow. That is not a slope stability failure, or this mud flow has been triggered because of the slope instability or as a result of the sliding of the certain mass. So there may be a combination of one with the another. Sliding might have caused the mud flow, but when this soil chunk has mixed with a lot of water, resulting in formation of a viscous fluid. Now, in our slope stability, we normally hear about the two things are the mode of the failure of the slope. One mode is rotational slide and another mode is translational slide. So this is a detailed description about translational and rotational. So translational means it can typically occur between materials of contrasting density or contrasting permeability, where if you look at the failure plane, the failure plane is nearly inclined or nearly horizontal up to a certain depth or up to a certain length in case of the translational failure. But in rotational failure, the failure plane is more or less like a circle. So the translational is most common form of the slide in soil, while this rotational failure also most common in soil mass. But translational is very common in shallow depth, while rotational could happen shallow or even deeper depths. So when I say shallow, so it is obvious that the loose material exists for a shallow depth, followed by there might be a denser material. So that's why it is said. So the translational slide might develop along a boundary between the two materials having a contrast in density at the permeability. Typical depth of the translation is 1 to 4 meter, and length of the slide is much greater. While here that length is absent completely in case of the rotational failure. So examples of the translational slides are debris slides, debris avalanches, debris flow, uh, and in case of the rotational slides, the movement of any soil typically falls under the rotational slides. So you can see in this picture, so the difference between the translational landslide and rotational landslide. So here you can see, if you look at the exposed surface, so it's like a inclined line. So that's why it is called as a translational landslide. So here also, so this is a landslide. So it is perfect. This is slump rotational slide here. And this is also multiple rotational slides. So this is something like a cascading effect. And this is also another rotational. So if you look at the failure surface, it is not inclined, rather it is something like a curvilinear. So these are a few features which are giving the glimpses about the translational failure and the rotational failure. So this is another example for the rotational landslide. There are different terminology. So, and a few more glimpses about the rotational slide. All these are fall typically under rotational slide. Now, so this is what we are discussing. So this schematic clearly explains the difference between the translational failure and the rotational failure. So in case of the translational, it is also called as the planar surface. So but this translational or the planar surface can develop when a soil mass moves or when the soil mass is of the frictional material or non-cohesive soil. If it is a cohesive soil, so normally it is dominated by the rotational failure. So as you can see here. So, but rotational of the two types again. So it can typically form a circular failure, the circular surface, or non-circular surface. So it can fail in any one of these modes. So circular surface can typically happen in case of the homogeneous soil, while if the soil is of non-homogeneous, then the failure plane may be of non-circular surface. And you can also see apart from the translational or apart from the planar translational, a combined slip surface where it is a combination of the translational plus circular as seen from the above picture. While the last one is a translational slip surface, this typically can happen in case of the infinite slopes. So this is a complete summary about different failure surfaces. First slide, it is divided into two things. So it could be a translational or the planar or rotational or cut. So rotational can happen for the finite slopes. So, and again, when we talk about the finite slope, so the failure plane or the slip surface might be above the toe, might confine to above the toe, or can pass through, or base failure or deep seated failure. So any one among these three can happen in case of the finite slope failure, either by the rotational, that is circular, or non-circular. While in case of the translational failure, that is a planar failure, so this can happen in case of the frictional material or the sandy material. So that can happen both in finite slope and infinite slope. So finite slope means if that slope is made with the sand, definitely. So if you go to Thar desert, so you can plentifully see the planar failure surfaces because where the height is different. While in case of the hill slope failures, that typically falls under infinite translational failure surface. So these are the a few factors that dominantly or overwhelmingly you might have heard about contributing for slope instability. The very first one is the soil type. So very simple. Are you dealing with the sand material? Are you dealing with the clay material? Or are you dealing with the combination of the soil, that is sand or sand, clay, sand, silt, so on and so forth. Then geometry of the cross section, that is height of the slope, slope angle, then moisture content, then pore pressure, additional loads, shear strength reduction, then vibration and earthquake. So these factors may individually cause failure of a slope or in combination. So for example, just assume a embankment of a certain height. So you may find that this embankment of certain height may be stable under static condition. But when there is an earthquake, so it may become unstable and thereby it may fail. So that means, so here height, that is geometry combined with the vibration or earthquake. Similarly, so of course, almost all the factors we can link with the geometry of the cross section. In fact, when we try to determine the height of the slope, so we need to take into account all these different factors. What would be the moisture content of that embankment of the soil which is getting compacted? Or is there any possibility of the development of pore water pressure? Or what purpose the embankment is used? So will it be used for the canal purpose or will it be used for the road or the pavement purpose? So what are the live loads, dead loads? Then is there any other factor that is causing the shear strength reduction? So these factors I have already enlisted in previous slides. You have seen parameters which are causing high shear stress and low shear stress. Then there are two causes so that can lead to the failure of the slope. Those are external causes and the internal causes. So external, so these produce increase of the shear stress like steepening or heightening of the slope. That means when you decrease the angle of the slope or when you increase the height of the slope. Then internal causes, so these which cause failure without any change in external conditions, like increase in the pore water. So therefore, the slopes fail due either to increase in stress or reduction in stress. So these are the two important things that you need to understand. So when you analyze any slope, so you need to pay attention for two things. What are the factors which are causing increase in the shear stress? So increase in shear stress means reduction in the factor of safety. Similarly, what are the different
Sir,
internal? Yeah.
sir, sometimes your voice get stuck, sir. Can you please repeat again?
Okay. Maybe because of the network problem. Okay, I will repeat. Okay. So when you try to analyze any slope, so you need to pay attention for both the factors. The factors which are causing increase in the shear stress and the factors which are causing decrease in the shear stress. Because both, one is numerator of the factor of safety, another is denominator of the factor of safety. So if there is an increment in the denominator, the obvious consequence is reduction in the factor of safety. If there is a decrement in the numerator, the obvious consequence is reduction in the factor of safety. So therefore, you need to pay attention to both numerator, that is shear strength, and the denominator, that is shear stress. So this picture explains completely about what is the factor of safety, how do you define it, what is shear strength, what is shear stress. Clearly has been shown. Instability occurs when the shear stress, that is tau, that causes the moment, that is the downward moment, has here it is been shown. So arrows of the orange color, arrows of the orange color, and this moment is happening against the resistance. That resistance is designated in the form of a shear strength. That is in the form of a shear, that is tau f. So therefore, the factor of safety is defined as shear strength upon the shear stress. Accordingly, the factors which causes instability may be divided into factors causing increase. This already we have discussed. Now, so based on this simple figure, or based on the definition of the factor of safety, so I can ask a simple question. Now, when we conduct any triaxial test, so are we determining the shear strength or are we determining the shear stress? Anybody can answer?
The shear strength.
Shear strength. Okay. So on
So
what
actually,
basis?
we use the shear strength parameters like C and phi.
Okay. So may I please know on what basis you are saying that this is shear strength?
So because the cohesion and friction are the only components that govern the shear strength.
In fact, as a matter of fact, even shear stress also governed by both C and phi only.
Sir, actually, while conducting the triaxial test, we conduct this test up to the failure. Sir, when we get the failure stress, then we can know from the Mohr circle that what will be the shear stress or shear strength.
Exactly. So when we try to determine shear stress parameters or the strength parameters in terms of the C and phi in the laboratory, we apply the load until the soil literally shears or the failure. That means when you are reporting the C and phi value, those are equivalent to the stresses which are causing the failure. That's why if you recall your Mohr-Coulomb failure envelope in the shear strength theory, we have discussed. There is something called as a Mohr-Coulomb failure envelope, that is inclined line, and any point below the Mohr-Coulomb failure envelope is stable. But any point above the Mohr-Coulomb failure envelope is not possible, because at the line itself, the soil has already failed. So therefore, there is no possibility that the soil still can exist above the line. Okay. Now, so shear stress means, say for example, now you are constructing an embankment, but this is not an overnight construction. It takes, say, a couple of months time to finish that complete embankment. So in the first month, say for example, you built an embankment over a period of 12 months. So in the first month, you put some load that causes some shear stress, not shear strength. In the second month, you increase the load that enhances the shear stress. Third month, it further enhances the shear stress. Fourth month, fifth month, so on and so forth until the 12th month. Now, at the end of the construction, so if you calculate the shear stress, which shall be lesser than the shear strength of the soil, which was determined by conducting the particular test, maybe assuming the unconsolidated undrained or assuming the consolidated undrained or consolidated drained, whatever the condition it is. Okay. Now, its application you already understood in the stress paths. Now, this also I explained. Suppose you are prolonging the construction for a period of 12 months. So you are understanding how the loading increment that causes a particular path of stress increment. That is called as a stress path. Suppose if you have applied some amount of the sigma 1 load in the month of first month, then we know the very first point of the Mohr circle. That is equivalent to that amount of the normal stress. Similarly, when you keep on increasing the height of the embankment up to 12th month, so then you at that time you reach maximum shear stress. But of course, if you do not have any idea, so then you may exceed the shear stress imposition more than the shear stress. That means you are imposing or putting the load on the soil which is more than bearable. So in between comes is now how to understand that one. So in between comes a parameter called as a factor of safety. So if you have a very clear attention about the factor of safety, we can easily understand at what value of the strength the soil fails and what is the exact load that you are applying on the ground. So this picture will clearly give you a fundamental idea. So if you look at the basic definition of the shear strength by the shear stress, so this is how it can be defined in terms of the parameters. Fs is equal to tau f divided by tau d. Now here tau f is linked to, so tau f is linked to, so the point directly on the Mohr-Coulomb failure angle. That means this point was determined by shearing the soil sample literally. And tau d means this is the shear stress that is getting developed because of the application of the overburden pressure. That overburden pressure is nothing but your normal stress, that is sigma. That is sigma. This sigma is nothing but your sigma. So this one. Okay. As a result of application of this sigma, what is the improvement in the shear strength? What is the improvement in the shear strength? Suppose, if you look at carefully this graph, so I have applied a normal stress of the sigma n, that is overburden result. Sigma is nothing but gamma into z. So this your sigma is nothing but gamma into z. So when I have applied a normal stress of gamma into z of this much magnitude, and this has resulted in this much amount of the shear stress. This much amount of the shear stress. Now, what is the shear stress at failure? That is the tau f. So still this much gap exists. Now this can act as your factor of safety. So this is the margin you are following for the factor of safety. Now here you can also understand. Suppose when I'm increasing the shear stress up to this point, then so my shear stress is equivalent to the shear strength. That means I'm on the verge of the failure. So at any point of time, so the slope can fail. Okay, so this might have given very good understanding about the difference between the shear strength and the shear stress. So if any of you has any kind of a question, please ask me right. So if something is not clear, so please pose a question. So there's no problem.
That that means shear strength is not a tau max. It is a tau at failure.
Tau at failure. Your tau d is tau that you are applying, and your tau f is at failure.
But sir, why we discussing about tau maximum from Mohr circle?
That we are discussing basically. Okay. See, suppose if I ask what is the application of this graph, so can we able to understand what would be the application of this graph? Anybody?
So can you please repeat the question?
See, based on this graph, so can I take some kind of the measures, or can I calculate something? So in terms of the practical application, basically, where do you use this graph first of all? This shear stress versus normal stress.
Sir, as you said, this graph is helpful to find the factor of safety at various points, sir.
Okay.
And also by sir, by looking this graph, we can say if tau is less than tau ff, then it is means it is a stable.
Okay. Okay. Any other?
Sir, this graph is used to find the shear strength at failure.
Okay. Yeah. This Mohr column envelope is nothing but shear strength at failure.
To determine at what strength the soil will fail.
Exactly. So let us look at. See what we do first. In reality, we collect the soil sample from the field. We bring it to the laboratory, and we will do UU test, or CU test, or CD test. As a result, what we get, we can able to develop the relationship between shear stress versus normal stress. That means, so we have arrived at this Mohr column failure envelope. This curve is with us. This curve is with us. Okay. Now, when you go to construction field, what basically you do, you will not deal with the C value or pi value. You will only deal with the imposition of the normal stress, that is sigma. That is sigma only. Okay. Now, at what normal stress, so the shear strength improvement is there. Okay. Or else indirectly, suppose if this is the maximum shear strength of this material, then what would be the maximum normal stress that I can able to apply? Okay, what is the maximum normal stress that I can able to apply? How? So this is nothing but your sigma, but this is defined as gamma into Z. I know the value of the gamma. Okay, so thereby once I know the sigma, I can able to calculate what should be the height of the embankment that can be imposed for this already determine the shear strength. Okay, now this is on the verge of the failure point. This is the maximum height that is permitted. But when you are taking the factor of safety, what you do? So you apply a factor of safety for this sigma. So as a result, your shear strength is coming down drastically. So suppose if the shear strength is this one, when you apply the factor of safety, so it will come to somewhere here only. So then your original normal stress to be applied is only this much. This much. So when the intensity of the sigma decreases, so obviously there is a decrease in the height. Thereby we maintain the stable slope. Okay, so these graphs are so useful for the forwarding movement as well as for the backwarding. So this is how you need to apply the laboratory results in the field calculations. All right. So this is further description about the same thing. So these are the, if you define the factor of safety as tau f by tau d, tau f is equal to c dash plus sigma dash tan pi dash. As I told, this tau f is determined in the laboratory by conducting the triaxial test. While on the other hand, there is tau d, that is shear stress, which is also again same designated with the same constitutive relationship of Mohr Coulomb, c dash d plus sigma dash tan pi dash. However, there are two parameters, that is c dash d and pi dash d. Those are called as a cohesion and angle of internal friction that develop along the potential failure surface. But obviously, the c dash d and pi dash d are always lesser than pi dash and c dash. C dash and pi dash are at failure, while c dash d and pi dash d are at that condition. So at that condition, for example, you might have heard of mobilized cohesion and mobilized shear stress. While C dash and pi dash are the C and pi at failure. So mobilized means it is the amount of the stress required just to initiate or trigger the failure. At that condition, the amount of the C and pi are lesser than C dash and pi dash. So where the soil has already failed. While often, now if you look at these equations, there are two terminology. So we are defining the factor of safety with respect to the cohesion and with respect to the angle of internal friction. Now, between these two parameters, which parameter is more reliable, which parameter is not reliable? So to understand that one, the factor of safety is further defined with respect to the cohesion. So that is FC dash is equal to C dash by C dash D, and with respect to the friction, that is tan pi dash by tan pi dash D. So depending upon this condition, we can assume any other condition. You can assume that the factor of safety with respect to the cohesion is equal to the friction. And when you say, or when you assume this hypothetical condition, and if you substitute the terminology, then we can say the factor of safety Fs is equal to the factor of safety with respect to the cohesion or with respect to the angle of internal friction. So Fs is equal to 1. The slope is in a state of impending failure, that is on the verge of the failure. Fs is 1.5 means it is a stable slope. So this is the very basic understanding about the slope stability, or the different definition, or the fundamental definition of the factor of safety, so on and so on. So I will stop it here. So maybe we can discuss about different methodology in the next class.